Good afternoon, everybody. Good afternoon, guys. Can you hear me? All right. So let's start, and please feel free to stop me at any time if you have any question. Can everybody see my screen? Great. My name is Erez Allouche. I'm the Trenchless lead for Stantec Consulting. I have about 30 years of experience in the trenchless industry in North America. Um, the first half of my career, for about 15 years, I was a faculty member both in Canada at the University of Western Ontario, as well as Louisiana Tech University, where I headed the Trenchless Technology Center. And over the past 11 years, I've been working for Stantec, leading the Trenchless practice in Canada. What I'm going to talk about today is making the right choice. When I joined the industry, it probably was like 1996 or so. Trenchless was very young. It was an emerging technology. Um, we have a few proven methods such as CIPP, but even HDD was just kind of an emerging technology at that point. Technology went a tremendous revolution and transformation over the past 30 years, becoming to be a mainstream set of methods that are considered for each and every project, pipeline project. Is that municipal or oil and gas or uh, electrical, etc. Um, the other thing that happened is we really have a great increase in the number of methodologies that are out there as innovation, technology involved. We saw new construction methodologies such as direct pipe, uh, pilot tube, auger bore coming in, but we also saw a lot of hybrid crossing between methodologies, right? So now there is almost a tool set or a toolkit for a designer to be selecting from. Geotech consideration and hydrology are key consideration where we're selecting the right method. Selecting the right method during trenching technology is typically uh, very critical for the success of the project. Normally, we are using trenchless for a location that we do not want to excavate. Furthermore, we're typically very deep and taking advantage of the trenchless nature of the methodology to go to areas that we definitely do not want to excavate in. However, when things go wrong on the trenchless method, the only way, or one of the almost only way to actually recover things is to open cut it. which they make things so much more complicated, so much more expensive. So selecting the right methodology is key in the design process. The other thing to keep in mind that Trenchless is our entire toolbox. It is not like OpenCut is one, maybe two method. We can plow it, we can excavate it. Trenchless box is an entire tool set, and we're going to talk about it. So we actually have the option to optimize it and select the right method for a given project. We will talk then about the selection of about different consideration, geotech, hydrology, some geometrical consideration, and then we're going to wrap up with several case studies. So in terms of the trenchless toolbox, we mentioned the fact that it became to be from a last resort type methodology where people used to go to trenchless where absolutely nothing else worked, or open cut was simply not viable, did not get any permit, to really the preferred alternative. Now, regulatory option, if you want to open cut a road or a creek, wetland, the first question will be, why cannot use trenchless, right? So we kind of went to a complete 180 degrees from being the last resort to the preferred methodology. Um, uh, it's important to know what is out there, important to understand your toolbox, and it's important to know the advantages and limitations of each method. There is no one size fits all in trenchless technology. When we're talking about a toolbox, let's name some of the methods out there. We have auger bore, but we also have pilot tube guided overbore, right? We have the pipe ramming, but we have the pilot tube guided version of that. I don't know how many of you work with down the hole armor, relatively new technology in North America. We have micro tunneling, of course, we have HDD, we have the direct steerable pipe thrusting that we see more and more. We have impact molding. And then, of course, on the larger diameter, we have the tunnel boring machine, we have the pipe jacking, sequential excavation method, and drill and blast. So for rock formation. So we do have a large number of methods to select from. And I'm going to just touch on a few of those. I'm not going to even going to cover all of them because there are too many. When we're talking about auger bore, probably the most commonly utilized method for road crossing, embankment crossing, is simply a steel casing that house the auger inside it, supports from above ground, usually on a truck. Our auger boring machine is simultaneously thrusting the steel casing into the formation, what excavating and the material at the face of it, and the auger within the casing convey the cutting to the pit. Typical diameter will be, I would say, even the smallest machine out there about 18 inches. 36, I would probably would say maybe 24. In terms of common, typical drive is in the 30 to 90 meter. Guided auger bore can go as far as 140 meter in optimal soil condition. Generally, you cannot really steer the methodology. We can do a little bit in terms of elevation, play with it a bit, but it's a non-steerable method. Of course, it's an open face, so we have very little face control, very little ingress control. We really like to use it above the groundwater table in cohesion soil. We can use like solid. We can actually use it for medium sand or as well, but we really don't want to use it under the groundwater table with loose sand, any kind of flowing soil. It's nothing but a nightmare. The other thing, if you're running into gravel, cobble or boulder, it's really become to be very, very difficult. Those large granulates get jammed between the auger and the casing, the thing break, thing twist, and it becomes to be very challenging. The other methodology that we are using commonly is pipe ramming. It's a truly a brute force methodology. It's a simple steel casing that is being aligned on a track across the embankment, and behind it there is either an air armor. This particular one is a nitrogen charge armor, S90, and we do nothing but simply using brute force to armor the casing from one side of the embankment to the other side. Uh, Pneumatic or hydraulic driving tool can be used. Diameter is typically in the 36 to 96. However, with special equipment, we can go very, very large, 12 foot, 144 inch for completed. Drying length is limited. It's only about 60 meter. A, we have a lot of friction. And B, it's very difficult to steer those things, if at all. So we can go so far. It can actually operate below the groundwater table. In that case, we literally swallowing the soil. So there is very limited overcut, low risk of over excavation. Normally, there is a lot of mechanical energy that go into those type of armor. We're talking here anywhere between 2.4 to 9 million pounds of force. Those are huge forces. And we want to make sure that the edge of the casing does not get damaged or buckle during the installation. So normally we reinforce it with something that's called a shoe, which is another steel ring or two that are welded just beyond the face. Normally we can accommodate medium to small to medium cobble and boulder by simply swallowing those. And then when we get to the other side, then we can go in and remove the material using auger, using air pressure, water pressure, etc. Down the old armor is a technology that is kind of picking up slowly, coming from Europe. It's using a pneumatic armor placed at the leading edge of the casing. So if we're talking about pipe ramming, you can see the air armor sitting behind the casing and simply pushing it in, right? And basically we are welding another piece of casing and keep doing that. Here the armor sitting right here. This is the armor sitting right behind the face. This is the pulverizing cutting bit in the front. And so the armor is sitting on the front and pretty much is being extended forward and rotating at the same time. So it crush whatever in front of it, pulverize it into very fine particle, essentially into dust, and then using air pressure, all of that cutting being conveyed back to the pit. You can see the setup right now, where you can see the support, the casing itself. We talk about that all the mechanism is internal. This is the shoe. And here we see 1600 cubic foot per minute air compressor, right? So a huge amount of air pressure is used to drive those kind of tools. It's really good it can go to solid rock, go to rock debris, cobble, boulder. It's pretty much pulverizing anything in its way. It's non-steerable and again limited to about 70 meters. It does require some resistance at the front. We cannot use it on clay or sand. It has to be something really hard, like hard or solid rock, cobble or boulder. You probably heard about micro-tunneling. It's really simply a fully automated form of pipe jacking, which combine a remote control, pressurized face micro-tunnel that's sitting on the front, and we can see the micro-tunnel right here. So the micro-tunnel in the front, and a jacking frame. So what we are pushing in the micro-tunnel, here we see the micro-tunnel itself. Behind it there is the motor and the electrical system, and behind that we start adding concrete pipe, right? And those get jacked. The micro-tunnel face excavate the formation, and then that material go into a chamber where it get fluidized. It gets mixed together with bentonite, and you can see this slurry line right here. So basically it gets turned into a slurry, mixed with bentonite, and then circulate back all the way to the pit and then out of that shaft and go into that. If you can see those two green spots up there, that's a separation unit. At that point, the cutting gets separated from the bentonite. The clean bentonite gets re-injected back into the shaft through those pipe and down the tunnel all the way back to the cutting head. And it's simply a bentonite circuit with the cutting head, excavate the material in front of it, turn it into a fine particle which mix with the slurry, transfer it under pressure to surface, separate the cutting from the bentonite slurry, and then the clean bentonite get re-injected, and it keep going like that until the project is complete. As we're moving forward, we keep adding pipe segment that are jack from the shaft. So all of those piping, the bentonite slurry line, the electrical power, the control, telecommunication, everything get disconnected. We put another section, reconnecting all the line, and keep going. It's very powerful technology. It's extremely powerful, very versatile. It can really manage a wide range of geological condition, pretty much everything with the exception of gravel and cobble formation. They have wide range of machine all the way from 36 inch up to about 10-foot diameter machine out there. So, and from 900 millimeter, 800 millimeter, all the way to 3.4 meter, probably the largest machine in North America, maybe 3.6 meter now. It can go all the way to 1,300 meter in a single drive. We can extend typically those drive length using something that's called intermediate jacking station. You can see in the red image one of those. Those are a bunch of hydraulic jack that been inserted every 100 meter and kind of help pushing the pipe in front of them and helping to overcome some of those friction forces. And when the jacking pipe itself is installed, if it's a two-pipe system, we can either it's a one-pipe system, we simply use that to convey whatever product we want to convey to it, or sewer. Or if we have a pressure pipe, we always can install a second pipe through the tunnel, and that pipe is the carrier pipe. I'm sure that all of you heard about HDD, invented in the 1970s, really started to pick up in the late 80s. Today, it's bread and butter for a lot of industry, of the trenchless industry, especially in the oil and gas, but also in a lot of municipal application for pressure pipe. It's surface launch methodology. It can be used to install pipeline, a single drive under highway, river, wetland, city block, whatever you want. It's steerable in 3D. Initially, we kind of using a steerable small diameter drill string that follow the design alignment from the entry to exit location. At that point, we are replacing the drill bit with a reamer that then pull back and increase the size of the bore. And continuously, we can actually continuously increase the size of the bore. If a pilot is anywhere between 4 inch to 12 inch, depending on the machine, the final size of the bore can be as large as a 54 inch. So we can go pretty large, probably a 48 inch, maybe even 54 inch pipe that go into it. We drive length can be very high. It's kind of excessive. It's 2,800 meter, depending on the diameter and geological formation. Again, it's a bentonite-based product. Bentonite is used for many application HDD. We continuously pump bentonite. Some of the drilling equipment, mud motor, for example, are bentonite driven. We're talking about we're pumping in between 1,000 to 1,500 liters per second to run those drill mud motor. We're also using bentonite to stabilize the bore, both by creating a mud cake around the formation, as well as by creating hydrostatic pressure that keep groundwater away from that cavity we're creating. We use the bentonite to carry the cutting or the spoil what we cut down there to surface. We use that to cool the electronics, so there is a lot of function. Bentonite is a key for HDD. Um, it's really ideal for cohesive formation, but also can be used for non-cohesive formation, can be used above and below the ground. Water table can be used in solid rock. Again, gravel, cobble, and boulder can be a real challenge, especially when we have thick bed that we're trying to go through. Um, keep moving forward. Let's talk a little bit about one of the newest member of the family here, which is direct pipe or direct steerable pipe thrusting. It's really simply a hybrid. We talk about those hybrid technology, and direct pipe is a prime example. What it is simply surface launch microtunneling. So it's a microtunneling machine that is launched in a very similar fashion to a HDD, right? So we went to talk about microtunneling before. We saw big shaft, and you lower the machine to the shaft, and you basically launch it at the whatever target depth from the shaft, and normally it actually goes straight. It can take some horizontal curve, but it will be launched from a deep pit. Direct pipe is actually launched from surface, and we have a microtunneling machine that simply is connected to a very long steel pipe, right? Then there is the thruster right here that grab the pipe and push it forward and starts advancing the microtunneling into the formation. So we can see here the portal, the entry casing right here. We can see the microtunneling behind it, and we can see the carrier pipe strung behind it. The thruster is right here. It literally grab the pipe and push the entire assembly into the ground while simultaneously the microtunneling excavating the formation in front of it. Very similar to what we showed before. There are all those bentonite lines. You can that running through the machine and through the casing pipe. You can actually see the line coming right here at the back. Those will be the bentonite circuit line, will be the power, telecommunication, control line, all coming right here. And as the machine coming here, then we will bring up the next pipe, weld it behind that one, and then, keep going, right? Um, it is steerable technology. It's a microtunnel. It's very accurate. Can be used for on-grid application. It can follow both horizontal and vertical curve. Some of the benefits of technology is that it's actually using a very low drilling pressures in all the bentonite circuits are internal, running within hoses. There is outside, there's a little bit of bentonite to reduce friction, but that's a very low pressure. So we don't need to have those very deep HDD. We don't have the risk of rack out. We can go shallow and much shorter crossing without the risk of rack out. Um, it's a one-pass installation. Again, it's a microtunnel, can address a wide range of geological formation. And the other thing to keep in mind, very different from HDD, you can see that both the equipment itself and all the pipe are all at the entry location. The exit location is literally a little pit, could be potentially, 4 meter by 4 meter for the machine to come out from. There is nothing there, just a small hole in the ground. Um, all the equipment, the MTBM, the thruster, the side boom, all the pipe, everything has its entry. So if you have a location that is highly constrained, that you can actually have a quick space only on one side, but zero space on the other side, direct pipe is an ideal solution. Any question? If you guys have any question or comment, please raise your hand or simply put it in the chat. So we talk about all those methodology. We talk about our toolbox, and let's now talk about some of the geotechnical condition. So the selection of trench technology is really depend on the anticipated geotechnical condition. Encountering very soft or loose soil loose soil, like a loose sand, fully saturated loose sand, can lead to a very significant consequences if picking up the wrong method in the form of sinkhole settlement. Um, there are other methodologies that have no issue with soft soil, but really going to run into issue and going to get jammed when running into very hard bouldery soil that can hold the progress, um, resulting in potential abandonment. We can see in those images here, we can see in the upper right corner, you can see that's actually a HDD pipe, a steel pipe. It's all get groove and damage. The coating is completely damaged from boulder. It was pulled through. That's a big issue. We can see here a big sinkhole developing due to the trenchless installation beneath it. It's probably an open face in some kind of a loose formation. We can see here a frac out from HDD when we don't have enough cover, or we have a very soft soil that cannot contain the bentonite internal pressure. Here we can see an auger bore, and you can see all the cobble and gravel coming in, very challenging and can result in over excavation. Therefore, the selection of a suitable crossing technique is really a base, and it kind of relying on sound engineering practice and judgment. The things to consider include geometric capability of the equipment, such as length, diameter, alignment, profile, expected geological condition, and as importantly, hydrology condition. For example, any kind of going underground with the table, and of course, any kind of artesian condition are a major consideration. That beyond that, of course, we have to consider cost, risk, and risk mitigation capabilities. Understanding the expected geotechnical condition is critical for selecting the most appropriate crossing method for some of the Trenchless technology, because some of them can really accommodate a wide range of trenchless of geotechnical condition. Others are very limited and can run into some real issue when you encounter condition differing to what initially was assumed. When we're talking about reducing the risk in trenchless, it's really a multidisciplinary and a collaborative approach. So you can see that we have the owner in the center. Yeah, we do have the crossing designer, regulatory, the contractor, the inspector, but of course the environmental and the geotechnical consultant, right, or engineer. If you look on the different step that in it, you see that geotechnical consideration are playing key role in multiple aspects of the cycle, all the way from terrain evaluation and route selection to the geotechnical site investigation, the trenchless design, and the contractor trenchless execution plan. All those are heavily based on geotechnical and hydrology input. It's really important that to keep in mind that in trenchless technology, risk management is operational philosophy, is the basis for everything that we are doing. Everything comes from identifying mitigating risk. When we're talking about the geotechnical assessment for trenchless crossing, we can see some other issue. You can see a rail track. You can see a large sinkhole beside the rail track, very big issue. Obviously, at that point, the track is shut down. A lot of questions being raised. We can see here HDD that go into fat clay, right? Very sticky clay. At that point, nothing works. The clay simply stick to the reamer, and it's really become to be just a huge ball of mud that turning in the ground, doesn't do much to you. So the question, geotechnical investigation, when you're designing a geotechnical investigation for a trenchless crossing, there are a few questions that you should have in mind, and you should kind of target your investigation to try and answer those questions for the best, for the best of your ability. First one is, what does the site setting look like? What kind of geohazard do we have? right? Are we having slope stability? Do we have a crest? Do we have artesian condition? Do we have flowing soil? We have underground water like a buried river? Do we have boulder? Maybe we're going into a bedrock soil interface. We have fracture rock and boulder. Do we have any kind of buried bed stream, gravel, and cobble? All those are really important. Nearby infrastructure. Do we know what is there? Any other buried pipe? Any other abandoned pipe? Any abandoned landfill? Contaminated soil? We really need to find all of that information ahead of time. What does the subsurface look like? What are the characteristics of the soil and the rock? Groundwater condition, the elevation, artesian condition, expected ground behavior. Is that actually a stable ground, or is that a unraveling soil, right? How it's going to be interact? How is actually the machine soil interaction when the machine or the Trenchless machine is cutting the soil? How is that going to look like? Hopefully it doesn't look like that HDD, because that is not very useful. Um, uh, there are any problematic soil? Do we have any kind of organic soil, right? Organic soil are problematic on multiple levels. They interact unfavorably with drilling fluid. They really make them ineffective. They're very soft. They're unstable. Do we have any of those along the alignment? How we can actually solve that section? Proposed trenches measured feasible, constructable. What are the geotechnical risks that cannot be avoided? And do we have a feasible method that actually mitigates those risks? So a lot of questions, a lot of important questions to answer. So there are different matrices out there that kind of basically identified the capability of this methodology. As you can see, I list the methodology that we spoke about: HDD, direct pipe, microtunnel, auger bore, pipe ram. Down the whole armor, we also call it DTH and pipe jacking. We can see key geometrical parameter, the diameter, right? Target or maximum drive length, minimum depth of cover, right? What is the entry and exit launch port? Is that surface launch or pit launch or shaft launch? The ability to deal with gravel and cobble is really not a Boolean. It's not 0 or 1. It's really about the gravel cobble content, right? HCD can deal with 5-10% of gravel boulder. We can even deal with 20%. You put it into a 30-40%, we prone to be a real issue, right? For direct pipe or microtunneling, we are okay with smaller particulate, but when we're really exceeding about 1/3 of the size of the cataract, at that point the cataract cannot cut it anymore, right? And we can run into some real issue. So there are detailed information is important to be able to evaluate the suitability of a method for a particular crossing. Beyond that, I have developed a little matrix that kind of help you to identify the suitability of different methodology for based on a ground condition. For example, if we have a auger bore, definitely is suitable for soft cohesive soil. If you have a stiff cohesive soil, it's fine too. Or if we have bedrock, quite a soft bedrock, particularly under 15 megapascal. However, in conditions such as sandy soil or gravelly soil, it comes to big question. We talk about, how much gravel, how big are the particulate? Are we above the ground table? Maybe okay underground, the groundwater table, non-starter. And then places we cannot go, period, right? If we have artesian condition, if we have bedrock over 100 megapascal, if we have large cobble and boulder, that totally exclude that methodology, and et cetera, in either methodology. Any question? You guys are quite crowd. So I'm going to just kind of hit a couple of case studies. And the first one is a crossing that we did for Trans Mountain, the Alberta River triple crossing. It's really interesting crossing, both from a geotechnical and trenches perspective. Originally, the plan was to have 3 auger bore. There are several obstacles here. One of them is the Alberta River that you can see right here. Then we have the main east-west CN rail track, and then we crossing Highway 5, right? We have to cross those 3. Initially, the thought is to put 3 short crossing, however, there's physically no space to do it. So we had to come with a method to cross all 3 in a single trenchless crossing. And the question was, okay, which one? On top of that, we have a huge elevation difference. We see right here in the valley, and then typically we kind of crossing the road and going into that very steep hill. They're almost 22-meter elevation difference between the two. We also have a very large spectrum, especially pretty much that crossing was a geotechnical book. Here in the valley, we have organic soil, part of that meandering river. Under the railway track, we have sandy, very soft sandy soil. Under the highway, we have gravel, sand, and cobble. And up here, we're just huge boulder and hard rock. So pretty much 400-meter crossing that have almost every geological formation incorporated into it. So we had multiple environmental constraints. We spoke about it. Very complex geotechnical condition, extremely tight work area. And after a very detailed evaluation, we decided to go with direct pipe, probably the only methodology that actually can overcome all of those constraints effectively. Anticipated geological condition, as I mentioned, we have sand and gravel layer. We have silt and sand layer, both loose to compact and compact to dense. We have some frequent cobble and boulder. I show you some picture of those boulders. Actually, you can see up here some of those boulders were actually the size of a car. We have organic soil and pit near the exit, right? So a nightmare, a total nightmare, and literally every 50 meters we have a different geological formation. Let's go back to our metrics, right? So we have cohesive, soft cohesive soil, high plastic layer, organic soil, peat. We have sandy soil, high percentage of sand size or large particle, clay under 25%. We have sandy gravity to gravelly soil. We have cobble. We have boulder. So when you start to look on that, okay, auger bore is not there, pipe ram, it's not there, pipe jacking, not there, microtunneling getting close, but really the only one that kind of cover it all is direct pipe, right? Now let's look on capabilities. It's 4018, so it's within the diameter range of direct pipe. It's within the drive length. It's 400 meters, it's below 1,000. Minimum cover was about 4 times diameter. We can go as shallow as 2 times diameter. We're launching from surface. We have to launch from surface. There's a huge boulder there. And we have 30 to 40% gravel, right? And yeah, we should be able to manage that with the right cutting edge. So I think that the direct pipe kind of meet all the requirement and potentially the best methodology. The project was completed successfully, and that really was a substantial success. Another crossing was Highway 5 near Clearwater, BC. That particular location, we have on the east side a colluvial sound down to about 2 meters. Was underlaid by some fluvial clay silt. And that was on the east side. On the west side, we have colluvial gravel down to about 4 meters. Initially, they tried to use auger bore. We spoke about auger bore earlier in the presentation, and literally within 15 meters, this thing got jammed, stuck, twisted, whatever you want. This thing was not going anywhere. Had to be abandoned. There was just too much of those large granulate cobalt boulder that it was making possible for open face auger bore with a whole bunch of light auger to go through. We went back to the metrics. We kind of reevaluated everything and decided to go with 42-inch direct pipe. You can see it in those images right here, the direct pipe with the uh, cutter head in the front. Um, let's go back into our metrics. What we're looking for is sandy gravel to gravelly soil and cobalt boulder. Yeah, we have pipe ramming here, right? So that's one potential methodology, and the other one will be down the hole hammer. Um, let's compare the diameter, 42 inch, 80 range. The drive length is 70 meter is acceptable. Depth of cover is 4 meter. So we actually as low as 1 time the pipe diameter. We're going to launch it from a pit, and it's suitable for solid rock, boulder, and cobble. And the crossing was completed successfully within less than 10 days using this method. Last case scenario, Edmonton, Alberta, Calgary, Alberta, crossing of Anderson Road at Deerfoot Trail. Many of you may be familiar with that. We can see the drawing on the right-hand side. You can see it's basically a drainage line that needs to go under the new embankment. That is the existing Deerfoot Trail. They're going to realign the roadway and add a large exit embankment right here. The formation that we are going for, it's a substantial amount of cobble and boulder. We're near the Bow River, so literally we are either in boulder, gravel, or sand with a little bit of clay near the exit. 85-meter long crossing that we're looking for is to put in a 42-inch or a 1050 millimeter steel casing. Anticipate geology, like I mentioned, dense to very dense gravel with silt and sand, transition to very stiff clay layer with cobble and boulder right here at the exit. Installation design above the groundwater table, fortunately, which is literally just above the groundwater table. And in the casing, we're going to have a 24-inch gravity drainage pipe. Very limited cover. Literally, this is the lane that's still open to traffic. We barely have 1.5 meter cover under the shoulder. So based on the installation geometry, anticipated subsurface condition, the installation tolerances, etc., we chose to use a pilot tube guided pipe ramming was selected. It did took a couple of attempts to push the pilot tube through it to get the design grade. Design grade was critical. It's a gravity system. However, after a couple of attempts, the contractor managed to put the pilot tube between tolerance and complete the installation using pipe ramming. Going back to our little metrics, and again, you can see that when we're looking for sandy soil, high percent of sand size, large particle, gravelly sand, boulder cobble, we have pipe ramming kind of eat all of those. Sorry for that. Eat all of those requirements. And from a Geotech is a suitable method. Now let's compare geometry. We are looking for a 42-inch, 85-meter long, 1.5 meter cover, launched from a pit, and must be able to handle gravel, cobble, and boulder. And again, pipe ramming, check all of those boxes. This was the right methodology, and the installation was successful. In summary, Trenchless crossing methodology should be viewed as a toolbox, and you guys now understand why, right? You really have to pick up the right method for the right crossing, or you risk failure. One need to select the correct method for the task at hand. A comprehensive understanding of the anticipated geological and hydrogeological condition, including key mechanical properties and the behavior of the soil when it's excavated, that machine-soil interaction play a key role in the construction method selection process. It's really not important what the pen and the paper are doing. Ultimately is what the steel blade and the formation are doing. That we have to understand that, we have to consider that, and we have to pick up the right method. We have to give the contractor the best chance to complete that installation successfully. A guideline developed based on an industry experience was presented and demonstrated via 3 case study that we just covered. In terms of the sequence of the evaluation, right? Carrying over only acceptable method. Initially, we're looking at Geotech hydrogen compatibility. Then we're looking at geometrical compatibility, and only method that kind of went to those first 2 screening tests are subject to comparable cost evaluation. Thank you very much. Any question?
Hi, Dr. Erez Allouche. Yeah. So sorry for a timely delay. So hello, everyone. My name is Nabil. I'm the CGS YP Knowledge Lead. So we had a bit of delay and interruption at the beginning, so I couldn't sign in, but we are here now. And I thank Dr. Erez Allouche for leading the event. So before we hop on, I do have some questions for Dr. Erez. Before we do that, I just want to give a very brief introduction about Dr. Erez. So as you were listening to Dr. Erez Allouche, he's currently the Trenchless Technology and Innovation Leader at Stantec, and he has devoted much of the past 3 decades to research and practice in the field of undergraduate infrastructure. His work focuses on the development of design models for underground constructions using trenchless methods. He specializes in the design of complex HDD and microtunneling crossings, and to date has completed the design and a construction oversight of more than 160 such crossings around the world. These installations have included crossings of major highways, railways, and rivers. His design experience also covers crossings utilizing other trenchless methods such as direct pipe jacking, auger boring, pipe ramming, down the hole hammer, and horizontal direct bores. Prior to joining Stantec, Dr. Erez was an associate professor of civil engineering at Louisiana Tech University and the director of Trenchless Technology Center. He is the inventor, co-inventor of 17 patents in the area of trenchless technologies and the author and co-author of more than 260 publications in the area of buried infrastructure management and pipeline installation using trenchless techniques. Dr. Erez is a former member of NASTT's board of directors. I would like to again thank Dr. Erez for your time for presenting. So, Dr. Erez, I do see some questions. If you kindly want, I can read them over.
Yeah, please go ahead.
Thank you. So, so the first question I see is Allouche Ahmed. He asked, can you please elaborate on the carrier pipe? What is it and when it is typically used?
Absolutely. So it's really a terminology, right? Normally, when we talk about trenchless method, we're talking about 2 types of method. One of them is a single pass method, and the other one are 2-pass method. So some of the technology that we have, such as microtunneling, for example, we can actually go ahead and install a single pipe. So we install the casing, right? We install that casing, and then when that concrete casing is there, we can put a secondary pipe within it. So that's called the casing, and then the pipe that actually convey the gas or the fluid, the liquid, is called the carrier pipe. So that will be a 2-pass method. Then, of course, we have HDD when we're simply pulling in the pipe that ultimately will also be conveying the product. That's called a one-pass method, and we're pulling in the carrier pipe immediately. We don't have a casing pipe that is installed beforehand. Is that clarify the question?
Yeah, I think so. Yeah, just yeah, and yeah, so yeah, I think it clarifies most of the part that was asking. So if you have still any questions, Elmoshi, you can certainly put it on the chat, or you can also email on the CGSYP email address, for the registrar's email address, and then you can share it with Dr. Allouche. Thank you, Dr. Allouche. There is another question from Mark Medella. So what is the best method to use on site with high groundwater table?
That you are dealing with a sandy formation, so gravelly sand, we're talking with clay till. So it's really a combination of both the geotechnical condition and the hydrogeotechnical condition. You cannot really separate the two, right? You have to consider both in order to identify the method that is more suitable. You can see you must consider your geotechnical condition in combination with your hydrogeological condition, right? I mean, can definitely tell you which method you cannot use. For example, auger bore cannot be used. Pipe jack cannot use, right? A lot of those methodologies that have an open face. However, in order to either establish the uh, constructability and suitability of other methodology, you do need to consider the geotechnical condition as well.
Yeah, yeah. Thank you so much,
And
Dr.
maybe
Allouche.
just one, yeah, maybe just more comment, one more comment. So it's almost the reverse process, guys, right? It's not that we are trying to pick up which method we can use. We're almost trying to pick up which method we cannot use, right? So it's actually working by a process of elimination. And then whatever remain on the table, then we can subject it to risk and cost evaluation.
Okay, I hope that answers your question, Mark. So I see a question from the audience. Uche, namely, you can unmute your mic, and then you can please ask the question too.
Thank you. Can you hear me?
Yes,
We
we do
can.
hear you.
Thank
Go
you.
ahead.
Actually, I appreciate for this last presentation to Professor. Very practical presentation and have many important informations. I just want to ask a question about pipe ramming. Pipe ramming, it doesn't require any shaft, but for example, for a pipe approximately 2 meters diameter, what is the diameter of the pit it requires, and does the pipe must be a steel pipe, and does it require to use bentonite injection at the same time? Thank you.
For sure. So several questions. In terms of the question, does that have to be a steel pipe? Absolutely. Pipe ramming can use only steel pipe. The amount of energy that is impacted by those hammer, we mentioned anywhere between 1.2, 2.4 up to about 8 million pound force. In air hammer, those blow are running at about 130 to 140 blow per minute, so 2 blow per second. Steel pipe is the only material that actually can withstand this kind of apply loading. In terms of bentonite lubrication, that really site specific. You can definitely use bentonite lubrication with pipe ramming. It will require you to weld a small diameter perforated pipe or tubes at typically around the crown or shoulder area. from where bentonite is injected into that small annular space between the pipe and the formation to reduce friction. If you are in any kind of cohesive soil, clay, particularly fight clay, it's much needed. If you are in sandy formation, it's really not required because the vibration from the hammer activity pretty much put the sand particle in suspension. So there is very little physical contact or radial pressure acting from the formation on the pipe itself. So it's really a function of the soil that you are in. And I'm sorry, I think I missed the question that you asked in the beginning, the first one.
I asked the diameters of the pit for 2 meters diameters of a pipe, for example.
Yes. So in terms of maximum diameter, so yeah, the largest one that I ever saw going in was about 12 foot or 3 meter. For those type of crossing, you have to use a very special hammer. It's called a hydrogen hammer or S90. Normal, typical air hammer typically will install casing up to about 96 inch or 2.4 meter.
So I asked the diameters of the pit, actually.
I'm sorry, the pit or the size of the pit, the size of the
Yes, the size of
excavation?
the pit. Yes,
Okay. So when it comes to the size of the excavation,
yes.
it's really depending on the equipment and the pipe. So normally it's the length of the pipe segment plus 2.5 meter, right? So if, for example, you are using a 20 foot, right, to a 6.1 meter long section, your pitch size will be in around 9 to 10 meter long. Normally, you need at least 1 to 1.5 D on the other side. So if you have trying to have a 1 meter diameter, for example, your pitch will be between 3 and 4 meter wide. And if it's a 6 meter long section, it will be about 10 meter long.
Okay, thank you. So it requires a big area when we compare it with the micro tunneling.
The pit itself, I mean, micro tunneling can be launched from a 6 meter diameter shaft, but you have to keep in mind all the area, all the equipment that's required to support it, right? Like in pipe ramming, all the equipment is sitting in the shaft itself, right? So we have that 4 meter by 10 meter, but that pretty much, besides that, there is not that much equipment that's required to support it, right? Micro tunneling, yeah, the shaft itself can be relatively small. I mean, we can go down to maybe 7 meter shaft or so. We just quickly find the micro tunneling here. So the shaft itself, that shaft right here, right, down river crossing, that maybe we can launch it from a 8 meter or 7 meter diameter shaft, but look on all the equipment that's required to support it, right? We need the crane, we have the separation unit, we have the generator, we have the water tank. So normally for a micro tunneling, a decent or average footprint will be 1,500 square meter for a jacking shaft and about 800 square meter for a receiving shaft. So yeah, the shaft itself is small, but then it's very much equipment intensive construction method. There is a lot of equipment on micro tunneling. Yeah.
Exactly, you are right. What may be the minimum thickness of the steel pipe for pipe ramming?
That really, you have to run the calculation to
Mhm.
establish that. It's a function of the drive length. It's a function of the mechanical characteristic of the formation, of the assumed friction is a function of the length of the pipe itself. of the pipe diameter. You have to take into account local buckling, compressive forces. So there, if you're going to look on AC have a pipe ramming manual which lists out the design procedure for pipe ramming.
Thank you so much. I appreciate.
You're welcome.
Thank you, everyone. I think we are about the end of the webinar now. So again, would like to thank Dr. Erez Allouche for your sincere presentation. We really appreciate it. And I thank everyone who had attended the webinar today. Just to let you know, these webinars are all recorded. And if you subscribe to our YouTube channel, you will be able to see the webinar uploaded within weeks from now, and then also you can access the past webinars over there as well. So thanks everyone, and I would like to end the webinar, and again have a great rest of the day. Thanks, Dr. Erez.
Thank you, everybody. Have a good day.
Good.